Here is a next example. Here in this question he's asking about find the resonant frequency of the given circuit. Okay, so that's a voltage source 10 Henry, 50 millifarad and 20 ohm resistors connected in series parallel combination. So first thing we need to convert, or we need to do, is we need to convert the given circuit into frequency domain. This is a time domain circuit, so converting frequency domain is nothing but converting everything into ohms. So here this is going to be a 10 Henry. A 10 Henry is nothing but J omega L. So this is J 10 omega. This is going to be 1 over J 50 milli times omega. So milli is 1000. So I mean 10 to the power of minus 3. If I take it to the to the numerator, it's going to be 1000 over 50 omega. So it's going to be minus, I'm going to leave the J in the denominator. Okay, so it's going to be 20 over J omega. Okay, now this circuit is in frequency domain. Okay, now to find the resonant frequency, what we need to do, we need to find the total impedance from the source point of view. So looking at the circuit from the source point of view, find the Z total. Once you find the Z total, find out the imaginary quantity and make the imaginary quantity equal to 0. So to find the imaginary quantity, so to find the total impedance, I'm going to do Z total equal to, you can see resistor and capacitor reactance, they are in parallel combination and it is series with inductive reactance. So it is going to be 20 parallel with 20 over J omega plus J10 omega. That's our total impedance. Now first I'm going to solve for the total impedance here, which is going to be 20 times 20 over J omega over 20 plus 20 over J omega. Let me label this as Zx. I'm going to find only Zx, this part. Zx equal to so here it's going to be 400 over J omega divided by 20 J omega plus 20 divided by J omega. J omega cancel, so it's going to be 400 divided by 20 J omega plus 20. So if I rewrite it, if I take it out, 20 divided, if I take out the 20 in the numerator, 20 over 1 plus J omega. Now my Z total equal to 20 over 1 plus J omega plus J10 omega. Okay, so I have 1 plus J omega in the denominator. I need to eliminate that J term in the denominator so that I can separate real part and imaginary part in the total impedance. So what I'm going to do, I'm going to multiply and divide this with complex conjugate of the denominator. So I'm going to multiply this and divide this with 1 minus J omega plus J10 omega. Okay, now in the denominator I have a plus b, a minus b. It's going to be a square plus a square minus b square. So 1 square minus J square omega square. We know that J square is nothing but negative 1. Okay, and 1 over J is nothing but minus J. Okay, so J is nothing but imaginary part. Instead of I, we are using J. I, we already use it for current. So in the numerator, I'll end up with 20 minus J 20 omega plus J10 omega. Okay, so here it's going to be 20 over 1 plus omega square. So the J term is eliminated, minus J 20 over 1 plus omega square plus J10 omega. Okay, so that's the real part and imaginary part. So you can see this is the imaginary part. To find out, we need to make imaginary part equal to 0. So at resonant frequency, imaginary part equal to 0. So the imaginary part I have minus 20 over omega over 1 plus omega square plus 10 omega equal to 0. So once I make that imaginary part equal to 0, so I'm saying this is resonant frequency, so we call this as omega naught since we are finding omega naught. So minus 20 omega naught equal to minus 10 omega naught times 1 plus omega naught square. Okay, minus get cancel, minus get cancel, and 20 omega naught 10 omega naught cancel, so we'll end up with 2. So 2 equal to 1 plus omega naught square. Okay, so omega naught square equal to 1, omega naught equal to square root of 1, which is going to be plus or minus 1 radian per second. Okay, so when it comes to frequency, number of cycles per second, so f naught equal to omega naught, or we know that omega equal to 2 pi f, so f naught equal to omega naught over 2 pi. So number of cycles per second, usually you don't have negative number of cycles per second, so we'll go with the positive 1 over 2 pi hertz. That's the resonant frequency for the given circuit. Now here is my question. So the given circuit has only 3 elements. It's a series parallel combination, right? Is there any way can I transfer this voltage source in series with inductance into a current source in parallel with resistor? I mean, by using source transformation theorem, I can do that. So I will end up like this. Okay, now this is not a current source, sorry, this is not a voltage source, this is a current source. V of S over to get that whatever that impedance value is, the capacitive inductive reactance. The inductive reactance I have J10 omega, Vs equal to Vs over J10 omega. Now remember, is this impedance, I mean, while finding your total impedance, does the source affect you in the previous example? So if you look at here, I do not care what was my source. Okay, I was able to find the total impedance without including the source. Now what happened here, once I remove the source, the circuit is completely different circuit. Now the resonant frequency for this circuit, we know that for parallel circuit is omega naught equal to 1 over square root of LC. If you use this formula, you will find the resonant frequency, but that is RLC parallel circuit. Okay, so you're not finding, it's a completely different circuit. So converting a given circuit by using parallel series combination method or by using source transformation method, transferring it into another circuit, that will not give you resonant frequency what we are looking for. Okay, so resonant frequency is, it varies once you change the circuit, once you convert that circuit into some other circuit. So my strong recommendation is never ever transfer the circuit by using source transformation theorem. So don't do this. All you need to do is find the total impedance by looking at the circuit from the source point of view, and then find the imaginary part and make it equal to 0 to find the resonant frequency. So never ever transfer the circuit by using source transformation theorem to simplify the circuit to find the resonant frequency. Never ever do that. Thank you.